You know, random access memory, or RAM, it's that invisible, super fast engine humming away inside pretty much everything we own. Our phones, our laptops, the giant data centers that run the entire internet. But have you ever really stopped to think about how it's made? I mean, how do we take something as basic as sand and turn it into one of the most complex, most precise things humanity has ever created? Well, that's what we're going to find out.
Because really, that's the kind of scale we're dealing with here. Modern RAM isn't just storing a little data. We're talking billions and billions of individual bits crammed into a tiny piece of silicon. And it can grab any single one of them in just a few nanoseconds. How is that even physically possible? You know, the simplest way to wrap your head around it is to think of a giant egg crate. But instead of eggs, each one of those little cups holds a tiny puff of electricity. If there's a charge, that's a 1. If it's empty, that's a 0. And that, in a nutshell, is a DRAM chip.
So, here's our game plan for this explainer. We're going to start with the core idea of just one memory bit. Then, we'll see how billions of them are controlled. After that, we'll dive into how they're actually forged from pure silicon, put together into the final product. And finally, we'll look at why this tech is so unbelievably important to our world.
Okay, so let's start at the very, very beginning. The absolute foundation of it all. The single, solitary bit of memory.
The design is actually brilliantly simple. It's called a 1T1 cell. That stands for one transistor, which acts like a tiny gate, and one capacitor, which is our little storage bucket. So to store a 1, the transistor gate opens up and fills the capacitor bucket with a charge. To store 0, it just empties it out. But, and this is a huge but, there's a catch. This is why it's called dynamic RAM. That tiny capacitor, it leaks. Like a bucket with a microscopic hole, the charge just fades away in about 64 milliseconds. That means the chip has to constantly, frantically race through and refresh every single bit over and over just to stop the data from literally vanishing into thin air.
Okay, so keeping track of one leaky bucket, that sounds manageable. But how in the world do you manage billions of them all leaking at slightly different rates and still find the exact one you need in the blink of an eye? Well, that's where the real magic, the orchestration, comes in.
It all happens in this incredibly fast 4-step dance. First, all the little wires, the bit lines, are set to a neutral, middle-of-the-road voltage. Then, a signal opens up an entire row of those transistor gates, and all the little capacitors share their tiny charge with the bit lines. Next, and this is amazing, special sense amplifiers detect this tiny, tiny whisper of a voltage change. We're talking millivolts here, and they amplify it into a full-throated 1 or 0. And then finally, that amplified value is written right back where it came from.
Now remember that last step I just mentioned, the write back? It might seem a little redundant, right? But it's there for a really crucial and honestly kind of mind-bending reason. The very act of reading a bit of DRAM destroys it.
This analogy here explains it perfectly. Think about it. When that tiny capacitor shares its charge with the bit line so it can be sensed, its own charge level changes. The measurement itself actually changes the state of the system. So the moment you read it, the sense amplifier has to immediately restore the original value by writing it back. If it didn't do that, your RAM would be a read-once memory. Pretty useless, right?
So, we get the theory. But actually building a device that can do this whole dance billions of times a second, well, that's a true engineering marvel. It all happens inside a place called a fabrication plant, or a fab, which are some of the most expensive and cleanest places on the entire planet.
I mean, the whole process is just pure science fiction. It starts by growing this perfect single crystal silicon ingot that's an incredible 9 nines pure. That's 99.9999999% pure. Then, using extreme ultraviolet light, they etch circuit patterns with features that are smaller than a virus. And it's not even flat. They have to carve these deep, three-dimensional trenches to build the capacitors, which are then coated with special films, literally one single atomic layer at a time. It's just wild. And here's the crucial challenge for engineers today. As all the parts get smaller and smaller, the capacitors also have to shrink. But if they get too small, they can't hold enough of a charge to be reliably detected. So what's the solution? You build up, not out. Engineers have to construct these microscopic 3D skyscrapers to maximize the surface area and keep enough capacitance. It's an incredibly difficult manufacturing problem to solve. Okay, so once these billions of cells are forged onto a big silicon wafer, that wafer gets diced up into hundreds of individual chips. But that tiny black chip isn't what you and I buy in the store, is it? So let's look at how it becomes the memory stick we're all familiar with.
This all happens on a super high-speed assembly line.
First, a machine basically screen prints solder paste onto a green circuit board. Then, these pick-and-place robots just fly, positioning the DRAM chips and other tiny components at a rate of thousands an hour. The whole board then goes through a 260 degrees Celsius oven, which is, about 500 degrees Fahrenheit, to melt all the solder and lock everything into place. And finally, a tiny little chip on the board gets programmed with all the timing data your computer needs to actually talk to the RAM.
Now that final testing phase is super important. It leads to a process called binning. See, even though they're all made on the same silicon wafer, not every single chip performs exactly the same. So they get tested for stability at different speeds, and then they're sorted or binned into performance grades. And this is it. This is where that expensive, high-performance overclocking RAM that enthusiasts and gamers love is born. It's from the best chips from each batch.
So, we've gone from a single atom all the way to a finished product sitting on a store shelf. But let's zoom out and look at the big picture. What is the global impact of this incredible piece of technology?
Well, first, let's just talk about the scale of the business. The global market for DRAM is worth around $90 billion every single year. It's one of the absolute cornerstones of the entire tech economy.
And the price to even get in the game? It's just staggering. To build just one new state-of-the-art factory that can produce these chips costs as much as $20 billion.
And that immense cost has led to some incredible consolidation in the market. I mean, just look at this. The result is that just 3 companies, Samsung, SK hynix, and Micron, control roughly 95% of the entire world's supply of DRAM. 3 companies.
And what does this massive industry power? Well, to put it simply, everything. The cloud, artificial intelligence, every PC and smartphone, the computers and self-driving cars, the 5G networks that connect all of us, none of it, not a single piece, works without high-speed DRAM.
Which leaves us with this one final, fascinating thought. We know CPUs are getting faster and faster, and our storage drives are getting bigger and bigger. But DRAM is that critical, high-speed bridge that connects them. As we start to bump up against the physical limits of how small we can make silicon, what happens when that bridge can't get any wider or any faster? Solving that memory wall problem, well, that's not just another engineering challenge, it's probably the next great hurdle for the entire future of computing.